Okay, so we have seen something that a smart transformer can do for the low voltage. Let's see what can be done, let's say, fairly easily. Okay. Easy and difficult is always a matter of comparison, but something that can be done with just a current control in the medium voltage. So, like yesterday I was saying that for the power electronics devices, the medium voltage might become like the next area where we can do everything. And also for the power system, something like that is happening as well, because distributed generation used to be connected just in the low voltage. Now, with more and more power, we have a lot of distributed generation in the medium voltage. Big photovoltaic power plants, they have the transformer, low voltage to medium voltage. Wind energy conversion system, they are already connected to the medium voltage. So, all the problems, let's say, that we are facing in the low voltage, where basically everybody can connect his own power electronics, computer, electric vehicle, we probably see all of these problems, some of them we're already seeing, in the medium voltage. So once nobody was using the medium voltage, or maybe just to connect some transformers to power some neighborhood, then medium voltage grid was kind of clean. But as it happened in the low voltage, connecting distributed generation and a lot of other things to the medium voltage is also causing problem over there. So, distributed generation. If we really want to have that the distributed generation is providing a good share of the energy consumption, or of the energy demand, then the distributed generation will be connected in the medium voltage more and more. So there is the need of the load management. There is now for the low voltage will also be needed in the medium voltage. The medium voltage is connected to the high voltage, and the high voltage is connected to the transmission, so the generators are connected there. So we can do some real damage if we don't do things accordingly. There is probably, and there will be, the need to support the frequency by means of the power electronics and by means of the distributed generation. We cannot just say, like in the past, okay, the distributed generation is small enough, it will have a negligible impact on the frequency. This, as actually we saw in the past in some cases, is not true. Once the distributed generation is more, the penetration is higher and higher, then we have problems. We can have problems. Well, voltage problems, we already have it. So the different power flows and increasing the penetration of renewable energy into the medium voltage, voltage violation in medium voltage are already detected. Reverse power flow is from low to medium is actually one of the causes, but there are many others. Let's just imagine how many wind turbines are connected to the medium voltage in Europe. A fault. A fault in the medium voltage, theoretically, is much more serious than one in the low voltage, because everything that is connected to the medium voltage grid will face the voltage drop. So there is the need to give voltage support in case of fault, to try to sustain the fault current, because at some point something will trip. This is how the protection of the power system are designed. we need to sustain the fault current long enough, millisecond, for the breakers to trip and then go back to normal. But in millisecond time, a lot of things can happen. So millisecond can be all right, or at least are all right now for the current, low voltage and medium voltage. But as Tao was saying yesterday, millisecond is not all right in an aircraft. In an aircraft, we're talking about microsecond. You have the fault, microseconds later, the fault is opened. So there is the need to assure a good power quality even in the case of the fault. This is actually a much bigger topic, because our power systems are designed now, our protections are designed now. Everything is based on the assumption that we have synchronous generators, transformers, and electromechanical breakers. So the way to trip on electromechanical breakers is to have a current 5–10 times bigger than the rated current to ensure that the mechanism, the magnetic part, trips. You already see there the problem, because providing 5 to 10 times the rated current for some millisecond, it is possible for a transformer that is made of copper. It's not possible for a power electronics device. If you have a power electronics device that is rated 300 amp, 3000 amp, maybe you can give it for a split microsecond, but not 1 millisecond. So with more and more power electronics that will be deployed into the grid, medium voltage, then also all this idea of protection and power system design will necessarily change. My opinion, of course. And one of the good things of a passive network made of transformers and inductors, capacitors without control is that it's very hard to get it unstable. So yes, we have to ensure that the frequency is stable, that the voltage is stable, yes, but once we start having high switching frequency power controllers with feedback loops, nested feedback loops, have you seen how many feedback loops a smart transformer has? We have stability issues. So, and this is caused by the converter. So, it is true that with power electronics, we can do much more than a conventional power transformer. It is true that power electronics is enabling the renewable energy harvesting. We couldn't do it without power electronics. It's also true that we are paying in terms of other problems. And the stability is actually something serious. If you have a full grid made of power electronics converters, and you don't know what's written in the firmware, you don't know which are the parameters of the PI regulators, it's a big unknown. So if you don't have some transformer or synchronous generator that is like making the system a bit slower to make it stable, then you really have to think of the stability of such a grid. And the stability where you don't have the parameters. So all of this, what does it mean? It means sensitivity analysis, robustness analysis, maybe H-infinity control. So all of these will be more and more relevant in the future. To design something to be robust against something that you have no idea how it's done. So the goal is that we want to have more and more renewable energy, and we don't want to change the transmission and distribution system. This is the trick. because we can always build new lines. Well, but it comes with a massive investment. It comes, and it doesn't solve the problem, because the lines, as they are right now, they are basically unused. 40–50% on average, it means that there is theoretically 50% more to be used before we start deploying another line. So it's just that we are not able to take the full advantage of it. The solution is not just buying something new. The solution is getting the maximum of what we have now. So why can we increase the penetration of the DG? Well, mostly because of voltage variation, so the voltage can rise. And at some point, it's hard to predict which is the effect once we are losing a big amount of renewable energy source power, which is the effect on the power system. So these are the main problems. So what can we do? Well, let's just have this. Let's just assume that some of the loads are supplied by the solid state transformer, by the smart transformer. So if the problem is like voltage rise, voltage control, then we have a fully controllable power electronics. We can do something about that. And also something that I was discussing with you a little bit earlier, it's not just the smart transformer that solves the problem. It's really all the scientists and engineers that are working on that are developing solutions. So smart transformer is a tool. Phase measurement unit, remote sensing, smart meters are another tool. Smart grids, another tool. So all of these at some point will need to work together. I mean, we are engineers. We know that there doesn't exist really the easy solution. Oh yeah, that's where the problem is. I change this and the problem goes away. No, the magnitude of the problem, the more I read on this, the more I think that the magnitude of the problem is really insanely big. So already, when some loads are supplied by some smart transformer, it is possible to perform voltage control. Then, for the compensation of the sudden loss, then is a smart transformer can help, but it can help as a tool. Somebody must tell the smart transformer what to do. And also, this is another thing that the smart transformer can do locally, is to provide some emergency control over the power. Because let's not forget that I have full control over the low voltage grid. Theoretically, if I reduce the voltage in the low voltage grid, I am reducing the power. So reducing the power, I can think of it as power control. Meaning I can also decide to increase the power. As long as I'm moving within the limits of the regulation, theoretically speaking, I'm free to do what I want. So smart transformer can provide emergency power control by interacting with the distributed generation, increasing or reducing the frequency maybe, or if there is some communication, I can also tell the battery packs, remote control of the battery packs by means of smart transformer. It's a possibility. So I can do a lot. I cannot solve all the problem by just changing a couple of transformers with solid state ones. But already like this, we can see where we can go. So let's just see. Something fairly easy, fairly basic. So main grid. Main grid means transmission. We have the high voltage to medium voltage, so this is our medium voltage feeder. So you see, we were so used to see a diagram like this for low voltage, but now more and more papers, power electronics paper, I'm not talking about power system papers, power electronics papers that they are showing something like this. So this is like the convergence. The power electronics, the control, and the power system are really converging together to help solving the problem of the future. So having more power by using more efficiently, more effectively what we have right now. So meaning is really some exciting time, I think. So we have a medium voltage grid and with all our feeder, and then we have wind generators. Okay, so this is something fairly typical in northern Germany where I was living. There are so many wind energy conversion systems that this is the usual case. So, which is the idea? The idea is that if we just have this kind of grid and with unpredictable power generation by the wind energy conversion system and unpredictable load by the load, we might have voltage violations. So the idea is that some of these loads, so load actually is medium voltage to low voltage transformer. A load in this schematic is a neighborhood, is an industry, is basically a low voltage grid. So the idea is that one of these guys will be substituted by a smart transformer, and the smart transformer will do something that is very simple. Power control. So if the voltage goes down, then I will inject capacitive reactive current. If the to actually try to lift the voltage up. If the voltage goes up, then I will inject inductive reactive power to take it down. So very, very simple. In general, all of these droop control, they are like preferred by engineers because it's kind of simple. Because you are very used to imagine generators connected together with some impedance. We like impedance. It makes us feel safe. So it is something that works, and I've been using a lot of droop controllers for this, for the aircraft. Again, as the complexity gets higher and higher, my opinion is that maybe the droop controller is really not enough. We might need to really go towards communication-based system and to have some really global optimizer to solve this kind of problem. But step by step. If I have a droop controller on a smart transformer, very simple implementation, I can do it without communication, is basically another block in Simulink. So very easy. What do I get? Let's just see. I change this load with a smart transformer. So if we don't have the solid state, so this was the bus 4. This is the turbines are on bus 4 and at bus 7. We are considering a plus minus 2.5%, and we are checking, do we have voltage violation? And all of these, there are different wind profiles and increasing power of the wind profiles. And all of these points, they represent the voltage at that specific bus. So the idea is that this is the case without a smart transformer. The maximum we can do is 7.5 megawatt, because otherwise we get a voltage violation at this point. If we have a smart transformer with this very simple droop control, same grid. This is actually the same grid. The only thing that I did was changing one node with a smart transformer. Of course, it cost some money. Again, it costs a lot of money because now it's not standardized. But if the smart transformer really becomes a technology with mass production, standard components, well, then the price will go down and down. Also, some people, they say, right, the price of the iron and the price of the copper will stay constant. Price of the copper can only go up. Price of power electronics is going down and down. So it is not too crazy, or anyway, it is possible at some point a conventional power transformer with a lot of copper will be more expensive than a smart transformer. Okay. In the future, we don't know. Let's just consider the PV converters. They were so expensive that both the panels and the converter, now the price went down, I don't know, 20 times compared to 20 years ago. So the price will probably not be a problem in the future. So same condition, same grid, just changing one component for another and adding some reactive power compensation with a line of code, a droop controller. Increase of 60% of wind power. So it's massive. It means that in that line, I can have 60% more of wind power just by doing this little thing. So there is really a lot of margin. So it means there are two things, that yes, the smart transformer is working, and second, that the actual infrastructure, it is not being used in the optimal way. So there is a very big margin of improvement. So anything is good, because if with something this easy as a droop control we increase by 60% the penetration, then it means that we can really do a lot. We see the light at the end of the tunnel. Another thing, we have the possibility to substitute the one of these smart transformer with the one of these load with some smart transformer. And the grid is a bit different. I have a photovoltaic and I have a wind farm. So how does it compare? Well, let's say in the case one, so let's just see what is case one. I have the smart transformer here. So 1 and 2 are high load, low PV, light load, high PV. So this is 1 and 2, they are these, and then I can choose, I see where is more effective to put a smart transformer here and there. So the voltage is still above the limit with at least 1 megawatt of solid state transformer. And this is, okay, 1 megawatt is a very reasonable value, because medium voltage to low voltage transformer, this is the usual size that we are considering. So in the case of heavy load and low distributed generation, then we need something a bit bigger. Why do we need something bigger? Well, because the distributed generation is helping, in some cases, to keep the voltage up. So when we have the problem, the cases are chosen in a way to actually show the problem. With high load and low DG, then the voltage will go down. With low load and high PV, then the voltage will be going up. So this is why we need control. So the idea of this study is to see that it makes a lot of difference where you place your smart transformer and which are the conditions. This is what I was saying, that in case of high PV generation, the voltage will try to go up. So in case 1, instead the voltage will go down. And the DG is not enough to keep this voltage up. Instead, with high PV and light load, all of these lines are going up. The same for where we put it. So in this case, 3 and 4, the position of the smart transformer changed. For case 3, we don't need a lot of power to keep the bus regulated. Instead, in case 1, we have the minimum power in this other load. So there are so many things to consider. High load, so the load can change. The distributed generation can change. The position of the smart transformer can change. This is why it's important to actually try all of these to understand which is the margin. Of course, I can come up with some simulation where I say, yes, in this very case, everything is perfect, but it's just one case. It's not what we should do. We should really try to get a sweep of all the possible cases, all the possible scenarios, or at least as many scenarios that we can simulate to really have the overall picture. So this is what this kind of analysis. We cannot just simulate 1 point. Meaning, yes, we can, but then we don't have the whole picture. Also because it changes with the time of the day. So, okay, PV is, let's say, quite predictable. At least it's very predictable that at night we will not have the PV. Load. Again, this load profile is something that considers that people, they go back home in the evening, and then there is the peak load consumption. It is true in some days of the year, in some areas, so even a sensitivity analysis on this profile should be carried on. And then the wind is this random, that depends on the location. On the seaside, you can maybe predict a little bit better, the wind flowing. But again, this is some reasonable variation, let's say. So we repeat the same analysis considering the daily variation. And okay, without the ST, then we have problems. We have voltage violation. Again, voltage violation, it means that some of those PV or wind, they may disconnect. So it's not just a violation because I don't like violation. It can really be a problem because at this point, maybe something gets disconnected. I have renewable energy sources, step variation that can cause ripples in the system. So it is important that the voltage is within the limits. Okay, one smart transformer is able to, in this case, with this variation of profile, is able to prevent the violation. So there is a lot that can be done. So this analysis was, of course, tried to cover several cases: high PV, low PV, high load, low load, different bus position, and in any case, the smart transformer helps. With a simple control, it helps. Even one smart transformer can make the difference and give much more possibility for DG penetration. So I think it is worth it to investigate this solution. Also because much more can be done. Harmonic suppression is a fully controlled power electronics converter. I can compensate for the harmonics. I can always decide to get balance, meaning I can absorb balanced three-phase current, but maybe I can also try to correct the imbalance that is existing in the actual medium voltage grid. Meaning I can decide for the smart transformer, it doesn't make any difference. I can draw the power from the different lines, different phases independently. It's not a transformer, it's power electronics. If the solid-state transformer absorbing imbalanced current helps to balance the medium voltage grid, good. So this was like something, again, this is something simple, but it is something that is not possible with other means. So if you have a fully controllable power electronics, then what happens in the low voltage in terms of imbalance has absolutely no effect on the medium voltage. So I can have all the imbalance in the world here, no effect in the medium voltage. Doing it with normal transformer, then they had to come up with connections, different types of winding to reduce this imbalance in the current. So it's easy with power electronics, it's very hard without. And then, of course, the smart transformer can control, we will see it tomorrow, how, can control the load connected to the low voltage side, changing the voltage, changing the frequency, or maybe using the communication. Then it could be also possible to, instead of, this is what I was telling, instead of controlling the stages independently, I can think to change the active power of the low voltage grid to control the medium voltage. So, many possibilities. I can have help for the frequency regulation, because if once I decide that I can control the active power, I can perform the load demand management to have frequency regulation. If the frequency goes up, I increase the power. If it goes down, I decrease the power. So I help the synchronous generator to stabilize the frequency. I can also decide to decrease the power when I'm in overload or anyway high load, and increase it during the low load condition. This CVR is something that it is done already with the tap changer, and is again simple idea, and I call simple ideas, sometimes it works very well. You are reducing the voltage. I mean, nobody really needs that the voltage is 230. It can be maybe 220. So this variation of the voltage, considering all the constant impedance load that are connected to the grid, maybe makes me save, I don't know, 5% of coal 5% of CO2 more. So, and again, nobody feels it. I don't feel it in the hair dryer that the voltage is 5% lower. But on a global scale, 5% can actually be a lot. And again, partial load shedding, there are many ways. Once you have the full control over voltage and frequency, there are many ways with which you can perform this. Lowering the voltage below the 5% limit. So all of these scenarios, we haven't written papers on this. I mean, there are so many ideas to develop that is, we don't have enough people or enough time. This is, very interested, I invite you to look into these topics. Yeah, let's say, a case of emergency load reduction, it should be developed. Should be developed more, this idea. But it is possible because you have the full control over voltage and frequency. The same for reactive power support. There are the references, anyway, all of these, Marco is going to distribute the presentation, so you find everything. So, for today, it's kind of finished.